We will now listen to Simon Kool of ILVO about how you can build a product-specific measuring method. And we include a demo, how to develop a new application from scratch. Simon Kool is senior scientist and also head of the Living Lab Agri-Food Technology. Also, specifically for this presentation, I would like to thank our colleague Bert Calles, who did a lot of experiments and processed a lot of data that will be presented today. Simon, I give you the word.
Yes, thank you, Karen. This is the content for my presentation today. I will present to you the results of our measurement campaign of soya and quinoa that was measured here at ILVO. For my presentation, I created the virtual scenario of a virtual food processing factory for which hyperspectral technology is used in 3 different stages of production in this factory. But first, I will give you a little bit more information on the measurement campaign and give you some visuals on how the data was captured and processed. Here you can see the first stage, of course, the growing of the product, which is then harvested within a harvester. Here you can see a little bit more about the milling process to go from the soy beans towards the flour. Here you see the different samples that were collected. This is the Kjeldahl method that was used to determine the protein content of the samples of both quinoa and soya. Here you see the measurement setup at our living lab to use hyperspectral camera technology to investigate the samples. Both a near-infrared and a visual camera were used. In this case, you see the application of flour. We also analyzed the raw beans. Here you see an application of a multispectral camera from IMEC, which was also used, but in the analysis. Here you see a lab-based high-end spectrometer from Anaspec that is scanning, in this case now, the flour. You see that the sample is rotating to perform multiple measurements on the same sample. Here you see the same result, the same process for the soybeans. And finally, we used also the spectrum sensor, which was already explained here before, to analyze both the soybeans, the quinoa beans, and the flour. Okay, then I would like to go a little bit more into detail in the application examples with our virtual scenario. In the first step, I want to focus on the incoming products. So use the spectrometer, in this case, the spectrum prototype, to determine the quality of the incoming product. So the question is there, is the quality of the incoming product within acceptable limits? We applied a threshold value of 40% in case of a soy flour to illustrate this process. Here I give you a little bit more information around the training of the model. So first, hyperspectral data is collected. In this case, with the spectrum sensor, of course. Reference data is collected. The hyperspectral data is pre-processed. So here you see an example of the raw reflectance curves colored by the protein level. And the next step, the reference data and the spectral pre-processed data are used in a regression or a classification model, which can then be evaluated, for example, by cross-validation or with an independent test set. And of course, the trained model, as Vincent explained already today, can also be used then in a real-time application. A little bit more information on how to evaluate a model. Some parameters here were already explained, so I won't go into detail. Generally, look at the R-square value, which gives an idea about the performance of the model and explains how much variability in the predicted variable is explained by the model. Another parameter that was explained by Johan is the standard deviation divided by the RMSE value. And this is the RPD value. So the higher this value, the better and the more suitable for quantification. Here you see the results with this device. So you see that very good results were obtained for the flour of soya. So we obtained a high RPD value and a very quite a low RMSE value, so a low error. For our virtual thresholding value or virtual screening, we see that almost all samples of the test set were predicted correctly as lower than 40% or higher than 40%. There were some samples misclassified, a low amount, but this is mainly due to the fact that the percentage was very, very close to the threshold level. The next setup that we want to discuss is a lab-based setup. We want to accurately quantify the amount of protein in soya and quinoa. And the question is here, can we replace chemical measurements by a fast inspection system in the lab, of course. Here we used high-end spectrometers with a high signal-to-noise ratio, as you saw in the image in the video before. We used both the FOSS device and the AnaSpec device, which are both active in the visual and in the near-infrared region. Here you see the quinoa sample being processed and also a soy sample being processed. Here are the raw absorbent spectra. So in contrast to the spectrums here before, we talk now about absorbance. You see also underneath first pre-processing method normalization, which results in a little bit more interpretable result. Next, you see the baseline removal, the effect of baseline removal, which brings already some more differentiation visually. And then after mean centering, you see that clearly there are visual differences between samples with a high and a low protein content. Here is an example of many different models that were trained using the MATLAB toolbox, the PLS toolbox, and the model optimizer. In this way, we can evaluate very quickly a lot of different pre-processing techniques and evaluate, for example, the accuracy on a cross-validation error. Here you see a result for soy flour obtained with the FOSS spectrometer. You see that a very nice calibration curve is obtained. And you see also on the right that some outliers were present. These were removed by inspecting both the spectra, by looking to PCA, and also by looking at these statistics that are given here, but I won't go into detail about that. As explained by Vincent, it is important that you look really carefully to the spectra to remove outliers and detect problems. You see here the results for quinoa. Or quinoa, that data set had a lot of visual differences between the different samples. And you see clearly some very strange things happen for some kinds of quinoa. And this was done in most cases by, for example, black beans, black seeds, or white seeds instead of the beige colored seeds. Here you see the results you obtained with the high-end spectrometers to do the quantification. So you see that for soy flour, very good results were obtained, a very high RPD value and a low RMSE value. For the intact beans, the results were still usable for quantification. As you heard from Johan, and threshold value above 2 or above 3 as indicating a good performance. And in this case, I will go to the next to the last application example, the inline measurement of soy and quinoa using hyperspectral line scan cameras, which was here the research question. So hyperspectral cameras, two different types were used, both a visual near-infrared and a near-infrared sensor. In our application, of course, this was done in a controlled environment, but the same can be done, of course, above a conveyor belt in practice. A little more information on hyperspectral imaging. I won't go really into detail. In hyperspectral imaging, both spectral and spatial data is acquired, and you can visualize this in a three-dimensional matrix. X and Y are the spatial dimensions. The Z or the third dimension is then the spectral dimension. Each horizontal slice of the matrix represents an image for a certain wavelength, which can then be translated towards a spectrum, as you see in the right. Two different cameras were used. Here you see a little bit some examples about that. We used for the visual camera both an LED illumination system and a halogen illumination system and a halogen illumination system combined with a spectra filter to increase signal noise for certain regions. The main difference in the approach that we see with respect to a spectrometer is that there is an image processing step being done before the spectral pre-processing. Of course, to obtain a model which can then be used in an application. Here you see some examples about that. You see that hyperspectral imaging is, of course, obtaining spatial information, which is then processed by image processing. For example, region of interest, the cutting off the edges and removing using morphological operations, the boundary regions or the regions in between the beans. Averaging the spectrum of this result can then result in a spectral fingerprint, as you see in the right, as we know it from a spectrometer. Here you see some results before and after pre-processing. Here you see the same for the FX10 visual hyperspectral camera for soy flour. So you see that the image pre-processing is a little bit more easy, of course, because it is a homogenized product compared to the beans or to the seeds of quinoa. But the same workflow is applied and a spectrum is obtained. Here you see the pre-processed and the raw spectra again. You see that there are clearly some differences with respect to the protein content, which is represented by the color in these images. And here you see the results obtained with the sensors. You see that very good results are obtained using the NIR FX17 hyperspectral camera. So a high RPD value and a low RMSE value is obtained. This confirms what is present in literature, that the near-infrared region for this specific case is more important, and this was confirmed by our results. But still, depending on the illumination system that was used, useful results could be obtained also with the visual hyperspectral camera. So here to conclude, for our virtual food processing company, which was explained in the previous steps, and based on the measurements obtained in our measurement campaign for soya and quinoa, we can conclude that the X-Spectrum spectrometer shows really some opportunities to classify incoming products, and even can be used to do a quantification in the case of soya flour. High-end spectrometers can effectively replace the majority, for the majority of time, the chemical measurements that take a lot of time in the lab. And hyperspectral cameras for this specific application, especially in the near-infrared region, can indeed be used for inline quality estimation. And that was the end of my presentation.